Hello everybody, welcome to our third lecture on graphs. Today we will study traversal of directed graphs. In the first lecture we did basics of graphs and their representation. In the second lecture we did traversal of undirected graphs, and now we begin our lecture on the traversal of directed graphs. Directed graphs, as you may know, have got edges and vertices like in ordinary graphs, but the edges are directed. That means the edge from one vertex is to another vertex. Unlike in undirected graphs, where the edges connected the two vertices, this here, the edges are an ordered pair of vertices. So the edges earlier the edges are now directed edges, and therefore as a pair it's an ordered pair. In any case, the successor function which we had mentioned earlier remains the same. This is an example of a directed graph. Here we have 10 vertices A, B, C, D, E, F, G, H, I, J, K. And as you can see, from A to B, the edge has got a direction. So this is a directed edge from A to B. All edges in a directed graph are directed from one direction to another. If there are edges between both of them, then there will be an edge from B to F and an edge from F to B. In general, an undirected graph can be represented by a directed graph by including edges in both directions. Directed graphs have also a special category. Whereas in undirected graphs, if there were no cycles, then they would form a tree. But in a directed graph, even if there are no cycles, they need not form a tree. Take this example. This is an example of scheduling where an expression is computed. For example, A and B are added here by this addition computation. The result is multiplied with C, and again here this result is added to E, and therefore both of them are added again together to get the final expression. As you can see that there is two edges coming into this plus node. However, there are no directed cycles. If this was an undirected graph, that is, this edge did not have a direction, then if this edge did not have a direction, then we would get a cycle. However, in an undirected graph, there are no cycles. Finally, a directed graph could also be a weighted graph. So there could be weights on the edges. So in terms of our definitions, we can have a normal directed graph as in figure 1. We can have a directed acyclic graph or DAG. So these are called DAGs. Directed acyclic graphs. They are graphs which contain no directed cycles, and there could be weighted graphs, or there could also be weighted directed acyclic graphs in such cases. We will study all these cases together and look at the traversals of all these cases. As usual, we use our basic traversal technique, which is the recursive technique, and as we have been doing recursive algorithms throughout this course, we will use the same recursive technique that we have seen in the undirected case. Here again we maintain, as we have shown earlier, we maintain a visited array which indicates whether a node is visited, and it is initialized to 0. As we had mentioned in the previous day, we maintain a parent pointer. So this is a parent of a node in the search. How is a parent defined? A parent is defined as follows. A parent, as we had mentioned in the previous day as well, A parent is defined a node parent of I is equal to j if there is a traversal from I to j and j was not visited earlier. That means in the algorithm, whenever what we are doing in the algorithm is as follows. As soon as we enter DFS of a node, we mark the node visited. This was before. Then for each vertex j, which is a successor, if it was not already visited, we were visiting it. But now we are adding this part to it. We are saying that we will mark the parent of j as node, which means the parent of I is j. If there is a traversal, this should be, let me just change it. If there is a traversal from so the parent of I is j if there is a traversal from j to I and I was not visited earlier. This is our case. So in our case, if the node j was not visited, then the parent of j is marked node and you do depth first search. So this being the case, let us now look at how we are going to do depth first search on this example and how that proceeds. So how are we going to do? Let us say we start from this node. If we start from this node, then we mark A visited as per the algorithm. Let us keep the algorithm at our side. We mark A visited. So whenever a node is marked red, it is marked visited. As soon as it is marked visited, there is only one directed successor of A, that is B, and therefore we go here and we mark B visited. But before entering, because B was not visited, we mark parent of B to be A. So this is the parent of B. I am marking the parents at the node. So the parent of B is marked as A, and we have moved from B to A. Let's make a little neater. So parent of B is marked A and we do DFS of B. As soon as we go into DFS of B, then we mark B as visited. And then there are how many successors? One is C and one is F. So we go to C, and first thing that we do is we mark the parent of, so parent of A is null. Parent of C is B, and we recurse and do DFS of C. Once we have done DFS of C, then we have these three children of C. One is A, but A is already visited. Then we have to go to E. We go to E and we mark the parent of E as C. Then from E, we can go to H. We mark H and we mark E as the parent of H. Then we come back from here. So we are going to backtrack from H back to E, and then we go to K and we mark E as the parent of K. From K, we move to J and we mark K as the parent of J. From J, we go to E, but E is already visited. So we backtrack up to here and then we come back to D and we mark D as visited, and before doing that, before entering D as visited, we mark the parent of D as E. From D, we go to G. We mark G as the parent of D as the parent of G. From here we go to I and we mark G as the parent of I. And then we go to D, but D is already visited. So we backtrack all the way from here. This edge is in this direction, so we cannot go this side. We backtrack from all the way to here. We back up here. We back up here. And then we had left to go to F. So now we go to F. And after we go to F, we mark B as visited. B as the parent of F. From F, so this way we have covered all the nodes, we have marked all the parents. And from the parental structure, we can find out all the nodes, all the paths from the nodes right up to the start of the search. So this is how we do a depth first search of this traversal tree. Let's go to a slightly different scenario. Let us say instead of starting at A, instead of starting the depth first search at A, we start the depth first search at D. If we start the depth first search at D, because we have not mentioned where we will start the depth first search with, we can start the depth first search from any place and let us assume we'll start it at D. If we start it at D, then D is marked visited, parent of D is null. Then we go to G, G is marked visited, parent of G is D. From G we go to I and parent of I is G and this is visited, this goes back and the search terminates here. As you can see from this DFS, unlike in an undirected tree where the edge is in both directions, if there was any connection, you would have continued the search in a graph that is connected undirectionally. But in a directed graph, even if there are many edges and all the edges and the graph looks connected, it may not be connected in direction. So we started from A and we reached all the nodes. We started from D, we reached only these three nodes. So we, as we have done in the previous undirected case, we have to write an outer loop. In an outer loop, we have to write for each node I, if visited I equal to 0, then DFS So this is an outer loop. So after completing this, we'll call it on another node. Let us say we call it at E. If we call it at E, then E will have null. From E we will go to H. H will have parent E. From H we will come back here, go to K. It will have parent E. From K we will go to J. J will have parent K. From this we will come back. From here we will go to D. And D is already visited. Now we will notice that there are two unique kinds of edges. One edge which was an edge which goes to a node which is not visited before and we mark them as a tree edge. Whereas if a node goes to another edge which is already visited before, then we mark it as a different kind of an edge and we will say that it is a cross edge. And we will define cross edges, tree edges, back edges and several kinds of edges in the next slide. But this also, if you see that this DFS terminates this way, so you will call it in the outer loop again. This outer loop will be written in the main program. This outer loop will be written in the main program. And then maybe we will call it here. If we call it from B, then B will have null. From B, we will go to C. C will have parent B. From here, we will go to this node, which is already visited. Then we will go to A. A will have parent C. From here, we will go back. From here, we will go to F. And F will have parent B. And now we complete all the nodes and we have done a depth first traversal. So you can notice that in this case, the depth first traversal required us to go through three phases. In the first phase, we did this one. In the second phase, we did these. And in the third phase, we did these. And all of them, if you start from A, everybody is connected. But if you started from somewhere else, they are not connected. So path finding, cycle finding, all of these have a slightly different ramification when we go to a directed graph. Now, to analyze directed graphs a little better, we start doing a little more numbering, or we start tracing the whole process in a slightly different manner. So we now add a few more markers into the search process to identify exactly how a node is exiting and a node is entering. Whenever a node is being entered, we mark it by a timestamp. When a node is being exited, we mark it by a timestamp. And therefore, in order to do that, we add a few more variables, which I am going to describe in more detail now. We already had our visited variable. We already had our parent variable. We introduced two more variables here. One is called entry I, which indicates the sequence in which a node is entered, and exit I, which indicates the time sequence in which a node is exited. And we maintain a number which is the global timestamp. So this is a global timestamp. So what we do in the search now is, as soon as we enter, we increment the global timestamp and timestamp the entry point of a node. Then we complete the search as usual as before. And then after seeing all the children, again before exiting, we increment the timestamp and then ensure that we are putting an exit timestamp. So just adding these two, we are now gaining more information about how we are doing the search. We will now look at this on this example. So what we will do is we will look at this example and show how we are entering and exiting nodes. So let us say we start from this point. So we enter this node, mark it visited. Num, which was initialized to 0, is now becoming 1, and therefore the entry node is marked 1. From 1 we go to B. We enter this node and mark the entry point as 2. From B we go to C. We enter this node and we mark its entry timestamp as 3. From C we go to E. We enter this node and we mark its entry timestamp as 4. From E we go to H. We enter this node and mark its entry time as 5. Now look at H. H has no other successor. Therefore, we are now exiting from H here in this part of the code. Since we are exiting from H in this part of the code, we will do an exit numbering of H. So num will be increased by 1 and the exit number of H is 6. Then we come back to node E, and node E is not yet complete. Therefore, we will go from node E to node K. And from node K, we will mark its entry number as 7. From K, we go to J, mark its entry number as 8. Now J has already, this is already visited. So we are going to return from J and we will mark its exit number now as 9. Once we have marked exit number as 9, we go back to K. And from K we are going to exit, so we will mark its exit number as 10. Now we go back to E, but E is not yet complete. E needs to go to D. So since E goes to D, therefore we are now entering D. And D's entry number is 11. From D we go to G. G's entry number is 12. From G we go to I. I's entry number is 13. I need not go to D because D is already visited. So I exits. Because I exits, therefore the exit number of I becomes 14. We go back to G. Now G exits back. Therefore the exit number of G is 15. Once we have gone to the exit number of G, we go back to D. And D has seen all its children. So D exits and its exit number is 16. Now we go back to E, and E has completed. Therefore, E goes and exits. The E's exit number is 17. From E, I go back to C, and C has completed. Therefore, C, because C has got this child, and this child, all are visited. So C goes back, and its exit number is 18. Once its exit number is 18, it goes back to B, but B still needs to see F. So now F becomes visited, and once F is visited, for F we have its entry number 19. Now F's child D is already visited, so we return to D, and therefore it has its exit number as 20. From D we go back to B. Now B has seen all its children. It exits, and its exit number is 21. It goes back to A, and its exit number is 22. So from this we have now seen, we have got the entry and exit numbers of nodes. We also now see from the sequence of these nodes, we can now identify various kinds of edges. We can identify edges which are of a variety of kinds, and based on this entry-exit numbering, we will be able to see very interesting properties. We will notice that from the entry and exit numbering, for any edge UV, the entry of U and the exit of U, the entry of U, it enters a node U, it enters a node V, it exits a node V, and then it exits a node E. Which means that in this case, it goes through the whole sequence of nodes and then exits a node. Let us go to our cases here. Let us look at node 1. Node 1 has got entry value 1 and exit value 22, which means that it was the first node to be entered and the last node to be exited. Which means that all the edges which came out of node 1 to any other node, if there is an edge, then that edge is either called a tree edge or a forward edge. The difference between a tree edge and a forward edge is as follows. A tree edge is an edge, as we had mentioned before. A tree edge is an edge when a visited node visits an unvisited node. A forward edge is an edge when a visited node visits another visited node, but it is a successor of the node in the tree. For example, in cases like this from this node A, so let's use a different color. From 1 to 2 is a tree edge. From 2 to 3 is a tree edge. This is because the numbering of 1 and 2 This numbering lies intermediate between these two numberings. Similarly, the numbering of 3 lies intermediate between the numbering of B. The numbering of C lies intermediate between the numbering of B. Similarly, this edge which we have is a tree edge. But this edge between C and H, as we shall see, between C and H is also a tree edge. So the whole traversal mechanism that we had done, this edge to this edge, and so on and so forth. Whereas this is a tree edge, 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 this is a tree edge. This edge is a forward edge. So we will mark it by a different color. This edge is a forward edge. It has the same properties. It comes to a visited node, but this node is a successor of the tree edge nodes. This node was already visited when we came here. When we came this way, it got visited and it came back, and we came back to this node, but this edge is a forward edge. Let us come to the other edges. So we have done tree edge and forward edge. Excuse me. Now we are going to talk about back edge. The interesting thing about a back edge is that in a back edge, a back edge between U and V is that U lies between V, which means that U is an edge which lies between V. So let us try to figure out where do we have a back edge. Let us go back to our example. Let us look at this scenario when we came from D to G to I and came back. Now, obviously, this edge is a tree edge because this is 11:16, this is 12:15. This is a tree edge. Now look at this edge. In this edge, this one lies between these two, whereas in this one lies between 12:15 lies between 11:16, whereas here from this side if we go, 13:14 lies between 11:16. Therefore, this edge is a back edge, and a back edge typically tries to identify whether there is a cycle in the node. So this node, this is a very interesting type of a node, and this node is called a back edge. So this is the back edge. I have marked black as back edges. I have marked purple as tree edges. And I have marked green as a forward edge. What are the other back edges? Let us look at another possible back edge. Look at the edge from J to E. The edge from J to E goes back to a visited node, and therefore you will see that J lies between E. So this edge is also a back edge. Back edges typically go back to an already visited node. And once you go back to an already visited node, then you identify that you are actually trying to get to what is like a loop. So we have now seen back edge, we have seen tree edge and forward edge. The rest is a cross edge. In a cross edge, the entry and exits overlap. The entry and exits overlap. Since the entry and exits overlap, then you get what is called a cross edge. So other edges which are not tree edges or forward edges or back edges are typically cross edges. And in order to identify various kinds of cross edges, we will see that if there are two independent trees and one is not a subtree of the other, we get cross edges. So these are the properties that we have seen of tree edge, forward edge, cross edge, and tree edge. The back edge, as we shall see, helps us to identify cycles. So based on this understanding of tree edge, forward edge, back edge, and cross edge, we now want to know whether one node is reachable from another node. We will notice that a node is reachable from another node if there is a path from a node A to a node Y. So if there is a path from node I to node J, which goes through tree edges, forward edges, or cross edges, then there is a path. Once a path has got a back edge, then we will know that there is a cycle. And as usual as before, we will be able to identify components in the same manner as we have done in the previous case. But here, finding components in a directed graph is a little trickier, and I leave it to you to identify how to find components. The next phase that we go to is a very important class of graphs, which are directed graphs, are called directed acyclic graphs. This was the example that we had seen, and we had mentioned what acyclic graphs are, that there are no cycles in this graph, which means that if there are no cycles in this graph, and if you can see what this graph does, at this point in the node in this graph, this computes A plus B. This computes A plus B into C. This computes A plus B plus E. And this adds this part and this part up here. So this computes A plus B into C plus A plus B plus E. So these are very popular and used in problems for expressing scheduling. How do I do these operations in an ordered fashion? And what we have to do is we have to ensure that we complete this operation before we complete this operation before we do this operation. We complete this operation before we do this operation, and so on and so forth. So this introduces what is called a precedence constraint. So directed acyclic graphs have one important property, which I think you may have already guessed. They will have no back edge. They will have forward edges, they will have tree edges, they will have cross edges, but they will have no back edges because there are no loops. Another important thing will be that there will be something called a root or roots, from where if you start, you will reach other nodes. There will be some nodes which are called leaves. A node is said to be a leaf node if it has got no successor. Because if every node has a successor, then you can prove that there will be cycles. Now, once we know that there are no back edges and no cycles, therefore, if there are no back edges and no cycles, then you have a mechanism to do what is called ordering. That means you can order these nodes in many ways. So we shall see how ordering happens. Two most important orderings are called topological ordering and level values. So one very easy way of identifying, so if we have to do this computation, then probably a sequence of computations could be, we look at A, B, then do this operation. After having done this operation, we can do this operation. So we can do this operation at step 1, then we can do this operation at step 2, then we can do this operation at step 3, and then we can do this operation at step 4. We could have also done this at 1, we could have also done this at 2, we could have done this at 3, and this at 4. Any one of these options would have been valid. We need to find any one topological order so that we know the sequence in which we will be able to do it. An easy way to find the topological order is to look at the exit values. If you look at this search, and if you look at this example, and if we try to find out the exit values, we will see how the exit values will happen. And the entry values and the exit values at this node will happen in the following way. This will enter 1, then it will go to 2, so this will be visited, this will be visited, this will be visited, this will go to 3, this will be visited, this will go to 4, then it will exit from here, so the exit value will be 5, then it will go to this node and we will enter this node, its entry value is 6, then it will exit from this node, its exit value will be 7, it will exit from this node and its exit value will be 8, it will come to this node, it will enter this node, its entry value will be 9, it will exit this node and it will come to this node and its exit value will be 10, it will come back to this node, its exit value will be 11, it will come here to this node, its entry value will be 12. From here it will go to this node, but it is already visited. It will go to this node, its entry value will be 13. Then it will come back out, I have made a different coloring, so I'll recolor this. Let me this entry value will be 12, this entry value will be 13, then the exit value will be 14, the exit value of this node will be 15, and the exit value of this node will be 16. For 8 nodes, there are 8 entry values and 8 exit values. You can now see, if you order the exit values, 5, then is 7, then is 8, then is 10, then is 11, then is 14, then is 15, then is 16, you will get the exact sequence of evaluation that we just mentioned. We will first evaluate these two, come here, we'll evaluate these two, come here, we'll evaluate these two, come here, we'll evaluate these two and come here. So topological ordering, you can take the exit values and just use the exit values to get a topological order. On the other hand, if you want to find levels, let us say what is a level? A level of a node, the leaf nodes are at level 0. Any node at a particular level is the maximum level of its children plus 1. So, the level, if you want to mark levels of nodes by a different color, then the level of this node is 0, level of this node is 0, level of this node is 0, and level of this node is 0. Level of this node is 1. Level of this node is 1, 0, the max plus 1. So level of this node is 2. Level of this is 1 and 0 plus 1, 2, and the level of this node is 3. So the level of the nodes also tell us, at what is the sequence at which I have to do these nodes. I leave it to you as an exercise to change this piece of code and include level. It is a very straightforward thing for you to do, to include in the recursion how to identify the level of a node. All you have to do is to define the level of a node. It initializes to 0, and here during the search, you find the maximum level of its children and add 1 to it, and you will get the level of that node. If it has got no children, then it has got level 0. Otherwise, it is the maximum of the level of all its children plus 1. I leave it to you to do the level value finding of a node. Next, we come to finding shortest paths in weighted directed acyclic graphs. In weighted directed acyclic graphs, the shortest path, since there are no cycles, the shortest path, there will be a leaf node. So this one is the leaf node. For this leaf node, if we have to find the path from A to I, so my source is A, and I have to find the shortest cost path from A to node I. So if the node is I, the shortest cost path to the node I is 0. What is the shortest cost path from the node H to node I? From node H, there are two paths going to node I. It will be the shortest path from this side, the shortest path from this side, the maximum of the two. On the other hand, D has got only one child, therefore the shortest path from D to I will be 4. Similarly, now that I have found D, based on topological ordering, I will be able to find the shortest path from H to I by looking at the shortest path from H to I, direct path, which is 3, the shortest path from H to D, and the path from D to I, which will be 4 plus 4, 8. So the shortest path here will be 3. Similarly, by a very simple recursive algorithm, I can find the shortest path in a weighted directed acyclic graph. We know we can write this down recursively as we have been doing so long. So we will find shortest path of node S to a node goal is equal to 0 if S is equal to G. Otherwise, you find out otherwise what you do is you find out the shortest path from all nodes which are successor of S to G plus the cost of, so this successor of S, let us say this successor of S is Ni, plus the cost of the edge from S to Ni, and you compute this over and find the minimum for all Ni element of successor of S. Which means that now I have got my recursive definition. The recursive definition says that if I have to find the successor from S to G, if S is the same as G, its cost is 0. Otherwise, I look at all successors of S which are Ni, and I find the shortest path from Ni to G. I add the cost of S to Ni to that shortest path, and I do it over all minimum, and I will definitely get the shortest path from S to G. For example, as we had seen before, this will be 0, this will be 4, this will be 3. This one has got only one child here, so this one will become 7 plus 4, 11. This one will take the minimum of 4 plus 4, 8, and 5 and 3, 8. And this one will get 8. And so on and so forth. And since this is a recursive algorithm, and this is very similar to the way in which we have implemented DFS, we can modify our DFS algorithm, put in the visited parts, and I will just leave it to you as an exercise to modify this algorithm and include this and submit this as an assignment. So we now go back to our recursive algorithms. All these algorithms that we have seen now, whether it is the depth first search, whether it is level finding, topological ordering, all of them are of the complexity of V plus E. It may be 2E, it may be something depending on the type of graph, but all the complexities of this will be of the complexity of V plus E. Finally, we come to breadth first search. Breadth first search is the same as we have done in undirected graphs. Yesterday in the previous lecture, by mistake I had written this as 1. Please note that this will be 0. Otherwise there was a typo in the program. Otherwise the algorithm is identical. All we do is if there is a loop, we have both edges on both sides. So the breadth first search algorithm, which we do in undirected graphs, is the same algorithm that we do in directed graphs. And I leave it to you as an exercise to try and work out the sequence by which we will be doing breadth first search. Finally, pathfinding in a weighted directed graph. Again, the algorithm is same, except that we had marked something initially as 1, which would have been 0. Otherwise, the algorithm is same. It is, as we had mentioned, as we shall see later, it is very similar or almost identical to Dijkstra's shortest path algorithm. So as a summary today, what we have done is we have identified the problems of traversal in an undirected graph. We went through the whole process of first defining directed graphs along with directed acyclic graphs and weighted directed graphs. We saw the basic traversal algorithm with the parent pointers and how to mark the parents. Then we showed that in order to do the complete traversal of the graph, we will actually need to have an outer loop to do all these nodes. Then we saw a very interesting feature of entry and exit numbering. From the entry and exit numbering, we found out that there can be 4 kinds of edges, and the fourth one is obviously the fourth one was a cross edge. So there are 4 kinds of edges. We also saw the properties of these edges based on the depth first entry and exit numbering. Based on these entry and exit numbering, we can now solve reachability, pathfinding, cycles, and components. Then we went to acyclic directed graphs, which has no back edge, and we found that we can now, from an acyclic directed graph, we can do various things like level ordering, topological ordering. We have a very neat shortest path algorithm for order V plus E shortest path algorithm through a recursive definition. We also saw that the breadth first search in a directed graph is similar to the breadth first search in an undirected graph. And finally, if we want to do in a weighted directed graph, we end up in a very famous shortest path algorithm, which we shall discuss in great details later on. Thank you very much. We look forward to the next one.